So, a team at Princeton just dropped a major breakthrough in quantum computing. It's a huge step, a really big deal for a stable quantum future. But what if the very physics they're relying on, the foundation of their success, is just wrong? Let's dive into what this hidden flaw could mean for, well, everything.
Okay, check out this number, 1.68 milliseconds. Now, that might not sound like a long time to you and me, but it has the entire quantum world buzzing. A team at Princeton, led by the brilliant Andrew Houck and Nathalie kept a qubit stable for that long. And trust me, in the quantum realm, where things happen at literally unimaginable speeds, 1.68 milliseconds is an absolute eternity. This is a gigantic leap forward.
And look, this isn't just some lab curiosity that'll get forgotten. It was published in Nature, which is a huge deal. This achievement really cemented itself as a massive milestone. They used the stack of tantalum on a silicon substrate, and it really looked like a clear win in the war against quantum decoherence. You know, that super annoying tendency of qubits to just lose all their information. But here's where the story takes a really sharp turn. A powerful new critique has popped up, and it asks a pretty staggering question. What if this whole success story is built on a complete misunderstanding of the problem? What if the enemy everyone's been fighting isn't actually the enemy at all? And this brings us right to the heart of the conflict, a hidden geometric flaw. See, this new critique argues that decoherence isn't really about making materials purer. It's about something much deeper in the fundamental physics of their design. So this slide really lays out the two competing ideas. On one hand, you have the standard model, right? This is what's driven billions in research. It says decoherence is caused by tiny, random chemical impurities or little defects. The solution? Just make everything cleaner and more perfect. But the geometric critique says, nope, that's just wrong. It argues decoherence is actually caused by a predictable physical tension between the material layers. And this right here shows the disconnect perfectly. The whole quantum hardware industry is building these insanely complex, ultra-high vacuum chambers to create perfect materials. But according to the critique, that's just a brute force approach. You're trying to solve a fundamental geometry problem by just endlessly polishing the materials, kind of just hoping that the natural strain settles in a way that works in your favor.
Okay, so to really get our heads around this, we need to redefine the main villain behind decoherence. Let's take a closer look at something called the two-level system, or TLS for short. All right, so in the standard quantum playbook, a TLS is the bad guy. It's this source of noise that just kicks a qubit out of its fragile quantum state. The key assumption here is that it's a random flaw, some tiny defect that, if you just try hard enough, you can get rid of by making your materials cleaner and more perfect. But the geometric view? Whoa, it completely flips the script. It says a TLS is not a random defect. It's a physical manifestation of stress, a predictable thing that's caused by the real physical tension between the different layers of the quantum chip. So it's not a bug, it's a direct consequence of the way it's built. So here's the absolute root of the problem. That tantalum film and the silicon substrate it sits on, they are fundamentally mismatched. They have a different, what's called constraint tightness. A good way to think about it is like trying to perfectly glue a sheet of stretchy rubber onto a hard sheet of glass. They just don't stretch and settle the same way. This creates a physical lattice tension between them that has nowhere to go, and that uncanceled tension is what physically becomes a two-level system.
So if the problem is geometric tension, well, then the solution can't just be better chemistry, right? It's got to be better engineering. And this new way of seeing the problem, it also suggests a really elegant, totally predictable fix.
The proposed fix is called precise amplitude tuning. So instead of chasing after these, phantom impurities, the idea is to apply a very carefully calculated static strain to one of the layers. You basically stretch it just right to cancel out that inherent tension, harmonizing the two materials so they play nicely together. And the proposed process is unbelievably direct. It's a three-step fix. First, you calculate the exact amount of strain you need to make the tantalum layer fit with the silicon. Second, you apply that exact strain while you're making it, maybe with something called a piezoelectric frame. And the result? The effective tension just drops to zero, and the two-level system physically vanishes. It's just erased. And this isn't just some hand-wavy idea. The critique even provides a specific formula to calculate the strain you need. Now, without getting lost in the math here, this equation basically tells engineers exactly how much strain, that's the epsilon symbol, to apply to cancel out the tension.
The fact that a formula like this even exists suggests that decoherence isn't a random problem, it's a solvable physics problem.
So, what's the big payoff for all this? The prediction is absolutely staggering. That record 1.68 millisecond coherence time, it wouldn't just get a little better. It would instantly scale up to seconds. That's not a small step. That is a 1,000-fold leap. It's a complete game changer for quantum computing.
So what we're looking at here isn't just another interesting theory or a new paper. No, this is a direct, profound challenge to the entire field's approach to building a quantum computer. And this challenge comes with an incredible amount of confidence. The critique flat out states that the math is absolute and, this is the most important part, it's 100% falsifiable. That means any quantum lab, including the one at Princeton, could do this experiment today. They can calculate the strain, apply it, and see for themselves if the decoherence is erased, just like the theory predicts.
And it all comes down to this final, really provocative thought. It's a bold statement that science doesn't move forward by agreement, but by testing ideas. So the question now isn't about defending the old model. It's about having the courage to test a new one, to run the one experiment that could prove it all wrong. And in doing so, maybe, just maybe, unlock the entire next era of computing.